Welcome to this vScaler demo. Today I'm going to be talking about HPC-on-Demand, and I shall run through a demonstration of spinning up a functional HPC cluster on our vScaler platform. So the first thing we need to do is just log in as our HPC-OD user. And what we get presented with when we log in is a summary of the resources that are being used within our project for the moment. Now, as we can see, there is nothing being used, so we have no virtual CPUs or RAM being used on the system. And we can also then just confirm that we have no previous networks set up or configured either as part of this deployment. So we can just see there's the public interface, which provides our external IP addresses, and then just this internal private network that I was using for Sahara testing earlier on. So what happens within a HPC cluster is we typically have a external network for users to remotely access the system, a head node which has all of the application software and configuration details for all of the compute node images, and then we've got compute servers as well, along with shared storage then across the system. So if we wanted to go and spin up a cluster, we have to consider all of those things if we were doing it by hand or doing it manually through a traditional infrastructure as a service platform. And within vScaler, we've provided a capability that allows users to go and do this themselves with minimal effort as well. So the first thing to do is we go to our vScaler tab and click on HPC clusters. Within this, we have a Create Cluster tab. Okay, so once you click on this, it presents you with a form that allows you to fill in some basic details for the cluster. So we give it a name and a number of compute nodes, and we select the cluster management system that we're going to be using as well. So once that's done, we can then select the node flavors. And when we say node flavors, we typically mean this is the amount of resources that are allocated to the VMs that run these services. So the number of virtual CPUs, the amount of RAM, the amount of disk, etc. So we have a HPC-OD compute flavor for those, and our SSH key then for remote access. In addition to this, we can configure additional storage. So if you wanted to add a parallel file system to the cluster, we can. But for this demo, we're just going to use the standard NFS share across from the head node. Okay, so once that's done, we can create the cluster and start the timer. So what happens in the background now is a number of networks are initially created to host the compute nodes and head nodes, the internal private cluster network, and routed network to allow the head node back out to the world. So we should be able to go into the network topology and see these being created. Okay, so you can see there's two additional networks that have been created since we came in here initially. We have this cluster network and we have a routed network. And we also have a head node that has been spun up as an initial instance. So the first thing that needs to happen within our cluster is the head node gets spun up and created. So this head node actually hosts all of our applications and software and configuration for the rest of the compute nodes within the system. So once this system is initially booted up, there's quite a few things that actually happen in the background here. Once the head node is configured, the rest of the compute nodes can then boot from that head node and pull down their configuration and mount the remote applications directory as well. So we need to give this a minute or two for it to spin up correctly. But once it's booted up and running, the rest of the compute nodes will launch then afterwards. A message gets sent back to our orchestration layer, and the rest of the nodes get instructed then to get created and spun up. Okay, so we can see now our head node has successfully booted up. It's taken 1 minute or so. That has all of the applications now configured and ready and running. And what happens now is our compute nodes get spun up and can pull down their configuration from the head node. So we can actually go back into our network topology. And we should be able to see a couple more systems now within our topology diagram. Excellent. So you can see our head node connected to the outside world, our compute nodes all connected to this internal cluster network. They should all be now in a running state, and we can go back to our cluster, and hopefully we should have a cluster create. Excellent. So we can see the cluster create complete, and we've also been allocated a public IP address for us to go and access this cluster as well. Okay, so we can now SSH into this cluster using the key that we provided before the setup, and a default user as well. Okay, so just to demonstrate that this is a working and functioning cluster, one of the most commonly used tools to provide sort of a user application environment to users is the modules environment. So we can have a quick look at all of the module files and applications that have been pre-installed and configured on this system. So we can kind of go from the top down here. We can see there's plenty of MPI libraries, BLAS libraries, numerical libraries. We've got Scala pack, Python, NetCDF, plenty of Python libraries, more MPI libraries, more maths libraries, the OR language, MKL, and plenty others. We've also got the easy build environment, so if there's an application here that isn't pre-installed or readily available, you've got this easy build environment to bring your configuration files to go and build any additional applications that you want. Yeah, after that, now we're just going to run a quick MPI job to show you that the cluster is fully functional as well. So I have a test Slurm script here that essentially runs. So Slurm is the resource manager. And typically within HPC clusters, you submit your application or workload to the resource manager, and that then farms out the workload across the available system so that you don't step on other users' toes in the process. So when you're submitting jobs, we'll submit to Slurm. Now what I might do actually is just add a sleep command to this job here, otherwise it'll run too quickly and we won't even see it in the queue. Okay, so now I can run the sinfo command, which will tell us all of the nodes that are typically available within our Slurm cluster or our HPC cluster. So we can see here we've got nodes 1 to 4. They're in an idle state, ready to accept workloads. So we can use the sbatch command now to submit our script to the HPC cluster. Excellent, so that's submitted okay. I can run sq, and we can see here now that our test Slurm has been allocated to 4 nodes. It's running on every single node. I should say as well, the program we're running is a very basic MPI application. So MPI is typically the parallel framework that's used for large-scale parallel workloads. But in this instance, we're just going to essentially run a host name on each individual system using the MPI run command for the benefit of speed. So hopefully now we should see that job has completed. Our nodes are back to idle, and we should have a output and an error file. So let's quickly check the error file. Excellent, no problems there. Check the output file. Excellent, so we can see that the node names have essentially been returned from that MPI run job there as well. So in that time there, we've spun up a cluster, showed you the modules environment, ran an MPI application, and actually, finally, so the next thing to do would be to actually bring down the cluster. So let me just exit out of here, and let's delete the cluster. Okay, excellent. So there it goes, created and killed in less than 6 minutes. But if I go back into the instances now, we should see them start to disappear. Just caught the end of the head node getting deleted there. The network should then be removed and cleared up. Excellent, and our cluster is gone at this stage. Great. So in that time there, we spun up a cluster, ran an application, shut it down again, and we can continue on with our day after that.